Thank you very much. In case there's any press in the audience, I want to emphasize that the impending collision of G2 and the black hole in the center of our galaxy is not the end of the world. So in contrast to the previous speaker, Romero, who talked about solar mass type black holes, those black holes which are probably collapsed stars and weigh only a few solar masses, I'm going to be talking about the black hole in Sgr A star, which is a million mass, solar mass black hole. And it's sort of the prototype for the types of supermassive black holes that we expect to have in every galaxy, in the center of every galaxy in the universe. I want to dedicate my talk to my PhD student, Yolanda Gomez. Here is Yolanda with her family in Thailand in 2008. This is Cecilia, who's an undergraduate at the University of Mexico now. And here's Vicente, who's now a graduate student in the astronomy department at Harvard University, taking after his father. So here's a copy of Yolanda's thesis, defended in 1990. The thrill of this thesis is I had to read it in Spanish. And then I had to sign this enormous book, which had the signatures of every thesis advisor at the University of Mexico since 1550 or something. It was a great thrill. But anyway, the thing, one of the things I remember fondly about Yolanda's thesis was she was one of the first to apply this technique of expansion. She looked at the planetary nebula NGC 6302 with the VLA at several epochs, and by careful calibration and analysis in the UV plane, she was able to actually detect the expansion of this planetary nebula, and with an assumed expansion velocity, she measured a distance to this object. So let me go on to today's topics. I'm going to talk about the accretion rate from the Faraday rotation measurements made at the submillimeter array, which are crucial to understanding the environment of the black hole in the galactic center. Then I'll talk about the VLBI imaging. There are attempts to actually see what the irradiation image looks like in the vicinity of the black hole. And finally, I'll talk about waiting for G2, which is supposed to be having an impact on the radiation from Sgr A star even as we speak. But it's my understanding is nothing has happened yet. So here's the scales on the galactic center. This is the logarithmic scale, linear scale here, a logarithmic angular scale. Here's the black hole represented at 1 Schwarzschild radius, which is about 10 to the 12 centimeters. And for a mass of 4.3 times 10 to the 6 solar masses. And that turns out to be 10 microarc seconds at about 8 kiloparsecs. So the key angular size to remember in this talk is 10 microarc seconds. It's a very small angular size. And you can only directly image that with VLBI measurements. As you know, the luminosity is only about 300 times the luminosity of the sun, or 10 to the minus 9 of Eddington. It's a very subluminous object, which is kind of mysterious. And the accretion rate is also unusually low. As the radio source surrounds the black hole at a radius of about some 10 times the black hole, and the stellar orbits are out here at 10,000 Schwarzschild radii over a range. And this area in between, of course, is an ionized plasma, which is the ionized accretion envelope, which may be a disk or it may not be a disk. So here we are in the summit of Mauna Kea. This is the submillimeter array here in what's called millimeter valley. This is the 8 6-meter antennas of the submillimeter array. Operates from 200 to 900 gigahertz. And although we can't resolve the black hole, we can measure its polarization properties and time variability quite accurately. So here's images that we get of the Sag A star at 230, 345, and 690 gigahertz. It's unresolved. This is essentially the beam size, and there's a little bit of a related emission around the black hole. And the important thing I want to point out now is that the lines here represent the direction of the electric field, the polarization direction. And you can see the polarization, this isn't quite taken simultaneously, but the polarization direction is different from 230 to 345 gigahertz. And that's a very important observation. And we can make use of the Faraday rotation effect to get the parameters of the region. So here's a typical night's observation of the galactic center, about 7 hours. The intensity at 230 gigahertz is about a Jansky, and it can fluctuate a fair amount, 50%. Here's the position angle of polarization, which can change quite rapidly on timescales of an hour, as can the percentage of linear polarization. So it's quite variable in its emission at 200 gigahertz, or about the 1.3 millimeter wavelength. So this was Dan Moroni's thesis, PhD thesis in 2005. This graph is actually essentially the sum total of his PhD work. Each one of these pairs is a night of synthesis imaging on the SMA. So what I've plotted here is the position angle of linear polarization, and here on the top is frequency, and the bottom is lambda squared, which is the appropriate units if you're interested in Faraday rotation. And the amazing thing is, although these are different dates going in the summer of 2005 over a several month period, and the interesting thing is, although the absolute polarization angle changes drastically over the period, the slope of the polarization change in angle between the two sidebands of the receiver, this slope connecting the polarization angle at the two frequencies remains nearly constant. And this is sort of a fiducial line and connects with the 345 gigahertz, but they weren't taken at the same time, so you really can't connect individual observations. But the slopes of these lines being so constant indicates that we have an underlying polarized source, which is exciting the plasma around in the accretion disk. And although the position angle of that polarization changes dramatically, the slope doesn't. And that indicates that the Faraday rotation is essentially constant in time, at least to the degree that these slopes are constant. So the theory is the position angle of the linear polarization should be the underlying input polarization position angle as the source goes through the ionized plasma, which is the accretion disk, the accretion envelope around the black hole. So anyway, taking the fact that we expect the position angle to change as lambda squared, if it's Faraday rotation, we can get out the constant of proportionality, which is the rotation measure, which is proportional to the electron density times the magnetic field integrated over the path length through the medium. The rotation measure turns out to be about -5 times 10 to the 5th radians per meter squared. And if you apply the normal theory with the assumptions that you have equipartition of energy between the magnetic and gravitational fields, that you have a power law density of material, and that you have an inner cutoff in the Faraday screen where the material goes relativistic and the Faraday effect is actually quenched. You put in all this and stir, you get an accretion rate of about roughly 10 to the minus 8 solar masses per year, which is remarkably low. If the black hole was accreting at this rate, it would take more than the age of the universe to come up to its current mass. So it must have had a much higher accretion rate at some time in the future, in the past, and maybe in the future. We're trying to do much better in this rotation measure. Here's also the position angle plotted versus lambda squared. We're trying to combine measurements with the SMA, the red point, and karma, 2 black points, and to see whether you can draw a straight line through 3 points. And if there's any deviation from the lambda squared dependence, you can use that to model the optical depth of the medium. But our first, we have a campaign we've just started last year. It looks like it is pretty linear over the frequency range of 230 to 345 gigahertz. This is an interesting curiosity. Another one of my thesis students, Dan Munoz, observed the circular polarization of Sgr A star at sub-millimeter frequencies. These are his measurements. And the interesting thing is if you combine that with the circular polarization measurements that have long been known from the VLA, the sense of circular polarization is left circular all the way from 1 gigahertz to 300 gigahertz. This is the fractional polarization, but this all has the same handedness. It's all left-handed circular polarization, which sort of rises to about 1% circular polarization at 300 gigahertz. Now, I find it really remarkable that Sgr A star could manage to say left circular over 3 orders of magnitude. And there is sort of a theory, which I'll just briefly flash in front of you to explain this. It's called Faraday Conversion, and this is a relativistic form of Faraday rotation. When you get into the inner part of the accretion flow where the material is ultra-relativistic, then the plasma modes are not circular as they are in a cold plasma, they're linear. And you get a phase shift between the 2 linear components, which has a phase shift which is proportional to the path length times the magnetic field to the 4th power times lambda cubed. And if you can make that phase shift exactly pi over 2, you will produce pure left circular polarization. But what you would expect is that since this phase shift is proportional to wavelength cubed, as you got the longer and longer wavelengths, this phase shift would change more rapidly, and you would get rather rapid changes between left circular polarization and right circular polarization. But you don't get that. It's left circular all the way down. And the way to explain this is through the optical depth effect. This is a tau equals 1 surface in synchrotron emission around the black hole. And that radius, in terms of Schwarzschild radii, goes from 6 at 230 to about 1600 at 1.4 gigahertz. So in other words, at low frequency, you only see down a little bit into the black hole, where at 230 gigahertz, you penetrate almost right to the black hole itself. So this means that at the low frequencies, the radiation comes from far out in the envelope of the accretion disk, and therefore the magnetic field is probably much less. It's decreasing its radius. So if you can conspire to make this tau equal 1 surface, which is basically the origin of the emission, conspire in such a way to keep this phase shift constant by tapping into a part of the magnetic field which is decreasing as you go out, you may be able to maintain a constant phase shift and therefore constant left circularly polarized. So before these measurements, if you looked at some of the models, it had the polarization rapidly changing from left to right. And that is definitely wrong. Any models of the accretion envelope has to preserve this left circular polarization at all frequencies and all time, but it's been that way for a decade if you look at the VLA measurements. Anyway, moving to the VLBI part of my talk, This is the original 2000 image of what a radiation from a black hole might look like. On the left side, if you have a maximally spinning black hole and a free-falling spherical envelope, the spinning of the black hole will give you a brightness on one side of the black hole, and that's caused by the radiation tracing through a curved black hole. So you can either look at the color contours, or this is the intensity. It peaks on one side, and there's a shadow in the middle. That's sort of characteristic of ray tracing around black holes. The bending of the radiation goes. On the other hand, if you have a non-spinning black hole, but the accretion envelope is rotating, now you're looking at an accreting envelope, and you see a bright spot on one side, and that's just the Doppler boosting of the radiation coming from material that's approaching you on the approaching side of the envelope. And this can be generalized. There's some really neat movies by Broderick and Loeb, which shows what happens if you have a specific discrete blob in the accretion envelope of a black hole. If you're looking at it face on, it just goes around, but if you're looking at it edge on, you get this tremendous Doppler boosting and the effects of lensing. Anyway, that's sort of a guideline of what the black hole should look like. It should be characterized by a shadow and then perhaps a ring around it. Now I want to give a little history lesson for the young folks in the audience. This is one of the magnificent results of the VLA. It's been around for 20 years, actually. This is one of the first results coming out of the full power of the clean and self-calibration technique of radio interferometry. So here we have another version of Cygnus A. It's a little more sharply defined than the one we saw of LOFAR this morning, but I was quite impressed by the LOFAR image because it had such lower angular resolution, being at such lower frequency. But this is characterized by a little emission from the core and then these two relativistic reservoirs of relativistic particles out here. Now, it always wasn't like this. If we go back to 1950, 51, there was a chap named Jennison and Dasgupta, and they were actually struggling to try to see what the structure of Cygnus A was. And they had a two-element interferometer in Jodrell Bank operating at 125 megahertz. So there was their base station at Jodrell Bank, and then they hauled their remote station out to these little villages, like you can read about Lower Withington, Hodge Hill, Gallsworth, and North Road. And they kept increasing the baseline to see if the source was resolved. That is, its visibility declined from 1. So the first thing they and other people found was that as you increase the baseline out here to 1,000 wavelengths, the visibility went down. So all you know that's happening there is you've got the source is resolved and you have a characteristic size. But they persevered and they went through the first null, and then the visibility started climbing up again. This is actually visibility squared, by the way, because they were only looking at intensity. That visibility climbed up enough that it ruled out a model of the source as being any kind of monolithic thing, like a disk or a Gaussian. And it could only be a double source where the components were slightly resolved. And it's always amazed me that Jennison decided to model this as two squares rather than two circles. So there's a galaxy in the center, two sources, which are those huge reservoirs of synchrotron particles separated by 1.5 minutes of arc. So I just show this as a lesson. This is where interferometry started in 1952, and 30 years later we get to these magnificent detailed images of Cygnus A. So we're going to a factor of 2,000 higher in frequency to 200 gigahertz. And we're sort of struggling at the same level that Jennison was so long ago. So there's a VLBI program that's led by a large consortium of different institutions. I like to think that it's a monolithic organization, and it is actually fairly monolithic. It's led by Shep Dolman, as sort of the leading spokesman. He's at MIT Haystack, and he's recently taken up a half-time position at the Center for Astrophysics. So what we have are stations in California, CARMA, the telescope in Tucson, University of Arizona, and various combinations of telescopes on Mauna Kea. We use the recording equipment at the SMA, sometimes the SMA antennas, sometimes the JCMT antenna, and sometimes the CSO. Our aim is to phase up all the sub-millimeter dishes on Mauna Kea and use it as a single dish, perhaps even as early as this year. So our initial data is confined to three baselines, a very long one, 4,600 kilometers, a slightly shorter one, 4,000 kilometers, and then the inter-US baseline of 908 kilometers. Before I show you the results, I want to make a technical aside here. The engine that's really fueling the rapid advance of very long baseline interferometry is the disk capacity versus time back in 1980 versus up to now. So now we're talking about disks of terabytes, where in 1980 we were talking about 100 megabytes as being a big disk. So the enormous increase in disk capacity has enabled us to grab enormous chunks of bandwidth to record and correlate, and that's greatly improved the sensitivity of VLBI measurements. Here's the cost of disks, which is really amazing. 1980, the cost, and this is dollars per gigabyte, so $1 million per gigabyte. Here's the year that it crossed 2005 is when it crossed $1 a gigabyte, and it's still going down. So whereas it used to be a terrible problem to record VLBI data, and very expensive, very clumsy, now you can record huge bandwidths of data, which makes possible working on very weak sources like the galactic center. Anyway, here's the fruits of our labor, a la Jennison 1952. This is a plot of the correlated flux density versus baseline length, except instead of being in units of 1,000 wavelengths, these are in units of a million wavelengths. So on a short baseline, we consider this the sort of the unresolved flux. There's a lot of stuff at the true zero baseline here, but that's probably unrelated to Sgr star itself. This short baseline between CARMA and Arizona probably represents the unresolved flux of the compact component. And then we have two groups. Here's the shorter of the long baselines, and here's the longer of the long baselines. So you can apply Occam's razor, and you can fit a Gaussian through there, and you get an angular size of about 43 microarc seconds. However, you can also fit a it's a Jink function, a Bessel-like function, which is a characteristic for a torus, or an annual source, which when smeared by interstellar scattering, plasma scattering, would look like that. So with the data that we have now, essentially 3 points, really, you can't distinguish between a smooth Gaussian source and a source with a hole in the middle, a donut. So what we need here is a few antennas in the middle of the Pacific Ocean to solve this. But we're seeking alternate solutions to that. So the size is 43 microarc seconds. You take out the plasma scattering. There's a little bit of plasma scattering still left. The intrinsic size of the black hole emission is 37 microarc seconds, which is only about 4 Schwarzschild radii. It's really quite amazing. The emission is coming from a region of characteristic size of 4 Schwarzschild radii. It was actually a donut. It's a little bigger, 105 microarc seconds outer and 48 microarc seconds inner radius. This just shows the plasma scattering as a function of wavelength. Here's the measured angular size. At the long wavelengths, the source is very big, and that's because of plasma scattering. This line here is a perfect lambda squared line, which describes the effect of plasma scattering. Some of it probably in the immediate vicinity of Sag star, and probably some just in the outer vicinity of the galactic center region. But anyway, by the time you get down to about 1 centimeter, the red dots are rising above. This is the red dots of the actual measured size. They're rising above the line. And these are our measurements. This is the red dots, the size. And if we take out the plasma scattering, you just subtract it out in quadrature, you get the green dot. So the green dots represent the intrinsic size of the black hole emission. This is our measurements, and this is a slightly dicier attempts to try to subtract the difference between the line and the red point. So our measurements up here at 230 gigahertz, 1.3 millimeters, show that the image is substantially the true image with only a slight bit of interstellar scattering. The intrinsic size has a wavelength dependence of lambda to the 1.4, which gave a thrill of excitement to the theoreticians because this is not untypical of jet sources. However, I should emphasize that there's really no evidence of there being a jet in Sag star. All we know is sort of its one-dimensional characteristic size. So here's the how things are going to develop in the future. We have this triangle here, California to Hawaii. We hope very soon to be able to add this critical antenna here, the so-called LMT, as soon as it's ready. And VLBI is one of the easier things you can do with an antenna when you're in the shakedown phase. So you can see that'll provide a lot of interesting intermediate baselines that will help us out a lot. And then we can extend to ALMA. There's a major project to phase up ALMA as a single dish to get a tremendous collecting area. And that will be one VLBI station. We'll connect with all these others. And then we keep going. There's a plan to renovate the South Pole station to be a VLBI station. So look at all these wonderful baselines that you get. And you'll be able to really start making Fourier transform images. You have to worry about how many stations can actually see the galactic center at the same time. So the European stations, Plateau de Bure and the 30-meter, really can't see Sag star. This is a view from Sag star. So early, you'll be able to use these triangles, and then later in the day, the Earth rotates, and you'll use the Western Hemisphere array. So this has been called the Event Horizon Telescope. Maybe that name will stick. I have a little flash of Greenland. That's for Paul Ho's talk. There's Greenland, a little bit over the horizon there. Anyway, these are 2 different model images that you might have based on different model considerations, but you have the black hole shadow in the middle, and then you have a brightening on one side, either due to the spin of the black hole or the rotation and accretion envelope. If you have 7 stations, you can start getting images like this, but when you have 13 stations, which will probably be possible within the next decade, you'll start to get fairly decent true images of what the emission looks like in the inner envelope. It would really be wonderful if you could see any deviations from general relativity, but it's so tied up in all the plasma characteristics, and I don't know whether that's really a reasonable goal or not. So my last topic here is to show the some of the expectations for the object that the Gensel group, which discovered it, called it G2. It's a cloud of gas which has about the mass of the Earth, which is in an orbit which goes very close to the center of Sgr A star. So here's this G2 cloud, and it's red is its predicted orbit. This was the position in the year 2000, before it was detected. These are all the stellar orbits that have identified of stars going around the Sgr A star. So I'll just show this in this animation here, which runs over about 30 years. So here we have it coming in. You can see the time, 2004. The galactic center is in here someplace. 2012, and so it goes around, and this is an idea of the tidal disruption that you might expect. So 2021, stuff is still flowing in, and then it's in a 100-year orbit. So the big question is, how accurate is this orbit, and how much material will really be tidally stripped off it? So there's the orbit. It goes somewhat inside the orbit of the star S2. So the closest approach is going to be about 2,000 Schwarzschild radius, velocity of 3,000 kilometers per second. And here's the mass of 10 to the minus 5 solar masses, the mass of the Earth about. If all that material accreted over 100 years, just say 100 years, that means you would have an increase in the accretion rate of 10 to the minus 7 solar masses per year over the ambient of 10 to the minus 8. These should be m dots here. Over the ambient of 10 to the minus 8, which I showed you we had measured with the SMA. So that might, you might expect a increase in brightening of a factor of about 10. So we might well see something. However, another model has emerged in which the, let me say, prompt emission comes from when the G2 plunges through the accretion disk, the putative accretion disk, which is thought to line up with one of the large-scale structures that we see in the stars. As it goes through the accretion disk, as it penetrates the accretion disk, it generates a bow shock, and you get relativistic particles and synchrotron emission. And so here's a spectrum of what you might expect in August of this year. This is frequency, and this is the flux density, and these are various different models of how the bow shock works and whether it's prograde or retrograde with respect to the accretion disk. This is the ambient flux density of Sgr A star. So the frequency of real interest is about 1.5 gigahertz. That's where the flux is predicted to be a maximum. And you can see it's 1 to 2 orders of magnitude over the ambience. So even this prompt emission could generate a huge effect later this year. And to try to anticipate this happening from a measurement point of view, the VLA is scheduling routine, I guess, director's time observations, which have been once every 2 months since October, and will commence this spring to be once every 1 month, July 2nd, June 2nd, July 6th. So here's what the spectrum looked like in December. This is just the part from 1 to 50 gigahertz where the VLA can make the measurements. These error bars are with the absolute 10% calibration measurement, but you see the sort of the relative calibration is much better. In October, it was 653 millijances at 1.5 gigahertz, and December 20th, it was 660 at the same frequency. Unfortunately, February, March, April, and May, they've gone to the D configuration, which is the most compact configuration. And there you have so much junk in the resolution beam of the VLA that you can't really see the Sgr A star by itself, but you get all the stuff around. So all they're able to say a couple weeks ago was the flux was less than 15 Janskis. So it's just a ridiculous limit. So starting in June, they'll move to the C configuration, which will resolve out much of the stuff around the galactic center, and they should be able to get close to the actual flux. But if this, you can see they can measure it to better than a percent or so, or a few percent accuracy. So if the flux were to increase by 10% or 100% or 1,000%, it would be easily measurable. So we're all waiting to see what happens to that. If anybody's interested, you can't read it there, but there is a public website where all this data is published, and our collaboration is going to be observing this with the VLBI starting in, well, we have a run coming up at the end of March. Unfortunately, at 1.5 gigahertz, you're well within the scattering. The radiation is sort of image broadened by scattering, so you have no hope of actually seeing this blob with the VLA or with VLBI because it's all just scatter broadened at this low frequency. Ironically, at the very high frequency, 230 gigahertz, where we're operating, the flux is just plunging way below the ambient, so there's no effect to be seen if you believe this theory. So it's probably going to be a difficult task to detect something, but it's quite possible. Thank you.
Even in the deconfiguration of the VLA, in the high frequencies, you will be able to more or less, at least at Q-band, you don't see mostly Sagittarius A, but the effect is small. So
right, they're measuring it at all frequencies of VLA, but you expect that most effect at low frequencies. If there is an effect, maybe this theory has a peak in the wrong place. Maybe you will see something at Q-band.
In the intensity of the center that you presented at the beginning, there were different inclination angles. Is the intensity changing with time, the inclination angle of intensity?
Well, we think that's characteristic of the rotation measure. That shift in frequency goes right into the lambda squared.
What about the cloud? How massive it is? Temperature? Is there any estimate of anything?
Well, in that original paper by Gillison et al., they estimated it to be about 3 times the mass of the Earth.
I think you said this. Yes.
Yeah.
And is it a hot or cold object?
I forget what the temperature is, but things seem to be proceeding as expected. This thing is being elongated and entirely stretched already, and the velocity is picking up as expected.
That's just the ionized part that you see.
That's right. I mean, it could be a star embedded.
If you look at the trail of the ionized gas that it detects, you actually see stuff downstream that has come in over time to suggest that in the back there's something more, right? So the amount of matter could be higher than what is seen at the moment, because he's just seeing the front end that's ionized.
But don't forget also that the accretion rate in the inner part of the envelope, as was measured, is uncertain by 2 orders of magnitude. So, there's huge uncertainties as to what could happen.
Yeah, precisely speaking about this uncertainty, I was wondering whether the polarization contains correction coming from gravitational wave radiation from the perturbation of the black hole.
Well, to be perfectly frank, I didn't think that the black hole perturbed the position angle of polarization. We're fairly far out. We're 1,000 Schwarzschild radii. In the outer envelope, but the inner envelope we're actually pretty close, where the radiation originates. But it's my understanding, I don't believe that the gravitational field changes the polarization. On the other hand, that could be responsible for some of the short-term variation. In other words, the polarization, the absolute polarization is changing rather rapidly at a time scale of hours, which happens to be about the orbital period of this thing. So if there was something tied to the orbital rotation period where you've got some oscillation in the polarization, you might be able to see it here. But that's probably more due to the magnetic field's alignment, that's locked to magnetic field's alignment.
Jim, do you know why is this second D array experiment so much worse than the first D array experiment?
Because I have mislabeled that. That is an A. Thank you. Sharp eyes.
Jim, is the orbit of this object well enough known that you know that it's actually going to pass through the accretion disk?
I'm not the right person to ask, but the original paper in January 2012 had the period of about 137 years. That got revised to something that came out just in February this year from 130 years to 190 years. And I think the innermost, the apogee point changed by 30 or 40%. So, things are right within a factor of 2.